In this video, we're going to design an orthogonal matrix of eigenvectors for a 4x4 symmetric matrix. So the symmetric matrix we're going to work with will be A equals 1, 2, 0, 0, 2, 1, 0, 0, 0, 0, 1, 2, and 0, 0, 2, 1. You can see, oops, sorry, you can't see. There we are. You can see that this matrix is indeed symmetric by noticing that that if you flip around the matrix along the main diagonal, the matrix doesn't change. Okay. Now, what we want to do, so this is the whole information we have, just a single matrix, and what we want to do is to make an orthogonal matrix whose column vectors will be eigenvectors of this matrix. The motivation for solving a problem like this lies in the theory of diagonalization, which is beyond the scope of the present video. But so for those of you who already know about it, you will recognize what we're doing here. For those of you who don't know about diagonalization yet, it will be beneficial that you first understand this, so that then with this understanding you will be able to understand that topic better. Okay, so let's see what we can do here. Well, the first thing is we are trying to create an orthogonal matrix of eigenvectors, and so the first thing is to find those eigenvectors. But before we can find eigenvectors, we have to find the eigenvalues. And to find the eigenvalues, we have to solve the characteristic equation, which in the case of this matrix is given by the following determinant being 0. So it's the same matrix as the original one, except that the diagonal entries are now the same diagonal entries as before, but lambda is being subtracted from the diagonal entries. All the other entries are the same as before. There we go. So we want this determinant to be 0. So we have to first figure out what this determinant is. Okay, so it's a 4x4 matrix. It's going to take a little while. Let's call this thing A minus lambda I. Let me write it like this: A minus lambda I. So it's the determinant of, it's fun writing upside down. The determinant of this thing is that. And so we can now start computing the determinant. So we can write down that a determinant of A minus lambda I is equal to 1 minus lambda times the determinant of the 3x3 matrix here, right? So it's going to be 1 minus lambda, 0, 0, 0, 1 minus lambda 2, 0, 2, 1 minus lambda. And then we have minus 2 multiplied by the determinant of 2, 0, 0, 0, 1 minus lambda 2, 0, 2, 1 minus lambda. And then we have, we're lucky here with the 2 zeros, so we'll have 0 times something and 0 times something else. And so in both cases there will be 0, of course. Great, so that's good. Less computations to perform. Okay. Now what we need to do is to compute those 3x3 determinants. So this is going to be 1 minus lambda multiplied by, okay, so let's see what we've got here. We've got 1 minus lambda cubed going in the diagonal like this, because 1 minus lambda has to be multiplied by the determinant of this matrix. Oh, so that's not just like as easy as that. So it's 1 minus lambda times, I think I need to use brackets here. There we go. 1 minus lambda times the determinant of this 2 by 2 matrix, which is 1 minus lambda squared minus 4, and I forgot about 1 minus lambda there. Okay, so 1 minus lambda times 1 minus lambda squared minus 4, right? And then we have a bunch of zeros again, and so that the calculation ends there. So let's just double check. What we did here is to multiply 1 minus lambda with the determinant of that. The rest of the terms in the determinant of this 3 by 3 matrix will be 0 because of the zeros there. And so indeed the determinant of this 2 by 2 matrix is 1 minus lambda squared minus 4. Okay, great. Next we have minus 2 multiplied by that determinant over there, and it's exactly the same story, except that now we have 2 multiplied by 1 minus lambda squared minus 4. Now, what we really do not want to do here is to expand out this polynomial. If we expand this polynomial out, we'll get a polynomial of degree 4, and we will not be able to know how to solve a polynomial of degree 4. In fact, there are formulas for polynomials of degree 4, which are kind of generalizations of formulas for polynomials of degree 2, except that those formulas are very complicated, and so nobody learns about them. And without knowing the formulas, discovering them from scratch might take a few months, or maybe just weeks, or maybe a couple of years. I've never tried myself. Anyhow, we do not want to start to work with a 4th degree polynomial if we can avoid doing that by not factoring things out. By factoring things out and not simplifying them. So we'll factor out some terms here, and we can see here that 1 minus lambda squared minus 4 can be factored out. So that's good news. And then the result will be 1 minus lambda squared, that's what will be left over here, minus 4, and this whole thing will be multiplied by 1 minus lambda squared minus 4. And look at this. This is fantastic, right? It's actually 1 minus lambda squared minus 4 squared. So you see, we get a very beautiful characteristic equation. The characteristic equation for that matrix is 1 minus lambda squared minus 4 squared equals 0. Okay, let's solve the characteristic equation. Well, to solve the equation, something squared is 0 means that that thing is 0, so we'll need to have 1 minus lambda squared minus 4 equals 0. And that gives us 1 minus lambda squared equals to 4, right? Which gives us 1 minus lambda equals plus and minus 2. And so what will lambda be? Lambda will be, well, when it's equal to plus 2, then lambda is minus 1. So that's lambda 1. And lambda 2 will be, when this is equal to minus 2, this is going to be 3, right? So it's minus 1 and 3. These are the eigenvalues of the matrix. And notice that even though we didn't expand this out, we can see from the form of this equation, because of that square there, that each of these solutions will have multiplicity 2. And this is where we can expect that the corresponding eigenspaces could have dimension 2. Okay, great. So now our next task, once we found the eigenvalues, is to find the eigenvectors. And to do that, we'll have to first go back to the matrix, see how it looks like, because now we're going to make a system of linear equations out of the matrix and the eigenvalues. So the system of linear equations that we'll have to make will be of the form 1 minus lambda 2, 0, 0. So this is the coefficient extended matrix of coefficients of the system, right? So that's the extended matrix. And what we need now is to take the values lambda equals -1 and solve the system for that value to get the eigenvectors for that eigenvalue. And similarly, we'll do the same thing then for lambda 2 equals to 3. So let's first work with lambda 1 equals to -1. If I put that value in there, the system I will get will be, so putting -1 minus -1 obviously will give me 2. It will be 2, 2, 0, 0, 0. Then the second row will be 2, 2, 0, 0, 0. And the third row will be 0, 0, 2 again, right? And 2, 0. And the last row will be 0, 0, 2, 2, 0. Right? So that's what lambda 1 gives the system. So we now want to solve the system by doing some row echelon business. So let us, well, let's keep the first row. And for the second row, let's just subtract, well, okay, so we've got identical rows here, so it's quite easy to see what's going to happen here. We can just put this as the second row because it's identical to the first one. And so the third row is this, and the fourth row is going to be that as well. Okay? That means what? What does that mean in terms of the solution K? So the solution we're looking for will be a 4x1 matrix, right? So it will consist of 4 entries, K1, K2, K3, and K4. And so if I had written out the system for this matrix, it would have all these coefficients in front of these Ks. And so when the matrix is in the row echelon form, then I read off the values of the Ks going from bottom up. And so the last equation here gives me 0 times K4 equals 0. So K4 can be any real number. And then once we know that K4 is any real number, then K3 from this equation is forced to be minus K4. And then K2 from this equation can be read to be any real number. And then K1 will be minus K2. So the eigenvectors for lambda equals -1 eigenvalue look like this. They've got some number s at the top here, so that's K1. And then, okay, maybe we can just keep it K1 and K2 kind of thing. So that's K1. If that is K1, what about K2? Well, now let's swap it around. Let's say K1 can be any real number, then K2 must be minus K1, right? So we can put K1 there, minus K1 here, and then once again, if K3 is any real number, then K4 ends up being minus K3. Where K1 and K3 simultaneously cannot be 0, and I can express this by saying that their product isn't 0. So by saying their product isn't 0, I'm covering up for the case that both of them can't be 0. And on the other hand, it's actually equivalent to it, right? So both of them can't be 0 if and only if their product isn't 0. One of them can be 0. Oh dear, what am I saying? Sorry. We don't want both of them at the same time being 0. One of them can be 0, right? So either K1 isn't 0, or K2 isn't 0, or both of them. So when we say or, maybe I shouldn't use either, because that might give an impression that only one of them has to hold. So when I say now K1 isn't 0 or K2 isn't 0, what I mean by this is either that or the other, or the possibility that neither of them is 0. That's in general how we understand or in mathematics. Okay, great. So what we want still is to get a better idea of the eigenspace. And to do that, I'm going to decompose this vector is a linear combination of two linearly independent vectors, so I can generate the the basis. So we can do this by picking any random values for k1 and k2, and then finding another set of values which would give me a vector that's linearly independent from the first one. So the easiest thing to do is to make k1 equals 1 and then k2 equals 0 as for my first vector, and for the other vector the other way around. So let's actually write this down. So the vector k1 minus k1, k3 minus k3 can be presented first of all as a sum of k1 minus k1 0 0 and 0 0 k3 minus k3, and then we can further factor out the k1s there, so it's going to be k1 times 1 minus 1 0 0 and k3 times 0 0 1 minus 1. Right? So on the other hand, these two vectors are linearly independent. And now that we have that any eigenvector is a linear combination of those two, which are linearly independent, I can say that the eigenspace is spanned by these two vectors, which happens to be also the basis of that space, because they are linearly independent. So what I can do in my kind of summarized solution for the eigenvectors, I could say that for the eigenvalue lambda equals -1, the eigenvectors are, and I just list two of them as a representative for all the others by simply taking their linear combinations, as long as we don't take the zero linear combination. If you remember, originally we wanted to create a matrix of eigenvectors which would also be an orthogonal matrix. And so for the matrix to be orthogonal, we want all those vectors to be orthogonal to each other. In this case, we are actually lucky, because if you look at these two vectors, they are already orthogonal to each other. If I take their inner product, it will be 1 times 0 plus -1 times 0 plus 0 times 1 plus 0 times -1. So the sum will be 0, and hence they're orthogonal to each other. Great. Now let's see how to get eigenvectors for the other eigenvalue. Which is eigenvalue of lambda equals to 3. So we go back to the original extended matrix here, where now we're going to use the lambda equals 3 eigenvalue. And so putting the 3 there will give the following matrix: -1, 2, 0, 0, 2, -1, 0, 0, 0, 0, -1, 2, and 0, 0, 2, -1. Okay? We still want to do the Kalon thing here. This time the rows are not identical, so the calculation will not be as easy as it was before. So we keep the first row, and then for the second row, what we need to do for the second row is that we multiply the first row by 2 and add it to the second row to replace the previous second row with the new one. So this will give us 0 here, and so we're multiplying the first row by 2, so it'll be 2 times 2 plus -1, which is 3, right? And then we'll have 0 and 0 there. So here we keep the third row because it's already it has as many zeros as we need for the row echelon. And for the last one, we do the same thing. Multiply the third row by 2 and add to the fourth one and write it in the place of the fourth one, which is going to give us 0. So 4 plus minus 1 is 3. And now, solving the corresponding system, we see that k4, so for the k now, k4 is forced to be 0, because 3 times k4 must be 0. And then once k4 is 0, k3 also needs to be 0. Does it? Yeah. Something is weird here, right? We can't get all zeros here because then it will be an eigenvector anymore. And then if k4 and k3 are 0, then k2, oops, we are getting zeros. I did something wrong here. What did I do wrong? Okay, so let's go back. Where were we? This is the matrix. This seems to be the correct one. Let me just double check with the top here. Yep, that's the one. And we were supposed to put in the, oh dear, it's not minus 1 we get here, right? Sorry about that. It's minus 2 that we get here. 1 minus 3 is minus 2, not minus 1. Okay. You see, I knew that I must have made mistakes somewhere, because I know that eigenvector cannot be the 0 vector. The existence of this eigenvalue guarantees there is a non-zero k. And so, since I was getting just the 0k, that's how I could detect the mistake. And then, of course, the row echelon is going to give something slightly different. Now we can just add. Oh dear, now it is as simple as it was before, right? Now we can just add the first 2 rows, and that will eliminate the second row. So this will stay 2 here, and here we'll have 0. And this will stay 2 here, and the last one will have 0. So then k4 can be any real number, because here you see in the last row we have just a row of zeros. So 0 times k4 is 0, and that makes k4 to be any real number. And then k3 and k4 must be equal to each other, right? If I bring this over on the other side, the signs will match. So k3 must also be k, the same as the k4. And then also k2 can be any real number, but not necessarily the same one. So then maybe we can keep track of these things. So let's call this k3, and let's call this k1, which must be, from the first line we see, must be equal to k2. So the shape of the k of the eigenvectors we have here is the first 2 entries are identical, the last 2 entries are identical, and either we've got here that either k1 isn't 0, and again I shouldn't write either, so k1 isn't 0 or k3 isn't 0. Okay, so now applying to this the same procedure as we did here, when we separated this out in this form, right, and we generated out of it 2 linearly independent eigenvectors, I want to do the same thing here to generate out of this 2 linearly independent eigenvectors. And remember, last time we were lucky, those 2 happened to be orthogonal to each other, and it seems like this time we're going to be lucky again. And it's not good to be so much lucky, because next time we might not be lucky, and then we would not know what to do next time when we're not lucky. So let's complicate the life a little bit. Let's pick not the vector here that would allow us to more easily get the orthogonal vectors, but a different one. So for k1, for the vector k1, we're looking for 2 linearly independent vectors. It's quite clear from this that the eigenspace here will have dimension 2. So for k1, let's pick the one that has 1s everywhere. And once we've got that k1, now we need a k2, and a k2 can be anything of that form, of the form k1, k1, k3, k3. These are small k's in here, and those are big k's, okay? k3, k3. And we want to pick the k2 in such a way that it will be not only linearly independent from k1, but also orthogonal to k1. And so one way to do this, I mean, there is a canonical way of doing this. We just pick any other k2 that's linearly independent from k1. In other words, that's not a scalar multiple of k1. And then we use something called Gram-Schmidt to replace that k2 with a different one. So we could have gone that route, but we can also go a different route where we directly write down what it means for the two vectors to be orthogonal to each other, and then get an equation which we can solve to determine the correct coefficients k1 and k3. So for k1 and k2 to be orthogonal to each other, what it means is that their inner product is 0. And so what is the inner product of those matrices? Well, it's multiplication term by term and then the sum, right? So the inner product is going to be k1 plus k1 plus k3 plus k3 equals 0. So we can pick any k1, k3 as long as this will hold. So we want 2k1 to equal minus 2k3. So what we want is, well, I just added the k1s together and k3s together, right? So we just need to pick k1 and k3 in such a way that k1 will be equal to minus k3. So what we can do then is to pick the following one. 1, 1, minus 1, 1, minus 1, right? And now we can double check. We take the inner product of those two. We get 1 times 1 plus 1 times 1 plus minus 1 times 1 minus 1 times 1. That gives us 0. Great. So now we've managed to identify for the eigenvalue lambda equals 3 two eigenvectors which are, as before, not only linearly independent from each other, but also orthogonal to each other. Great. What we do now is we want to combine these four vectors together in one matrix. So let's just keep it somewhere here to remember what they were. So these were for lambda equals, let me see, for lambda equals minus 1, right? Okay, so we will just put them in a matrix, but the problem is that we want this matrix to be an orthogonal matrix, right? And for that we want any two vectors in the matrix to be mutually orthogonal to each other. Now we already have that among those two they are orthogonal to each other, and among these two these are orthogonal to each other, but are they orthogonal to each other across? Now the thing is that for symmetric matrices, something that comes from the theory, for symmetric matrices, if you have eigenvectors for two different eigenvalues, they will always be orthogonal to each other. So any of these two eigenvectors will always for free be orthogonal to any of the eigenvectors here, and you can even check that by taking the inner product and seeing that you'll actually do get a value of 0. So we don't have to worry about making these vectors orthogonal to each other. All four of them are already orthogonal because per eigenvalue we made orthogonal choices, right? So across eigenvalues we don't have to bother, because for any symmetric matrix across different eigenvalues the vectors will always be orthogonal to each other. But we still have to bother about another thing, which is to make sure that the lengths of these vectors is 1. And so if I look at these vectors and I want to find what their lengths are, actually let's do this carefully. So what is the length of a vector? The length of a vector is given by it's given by the square root of its inner product with itself. It actually comes out as from a generalized Pythagorean theorem. Okay, so let's start computing the lengths of these vectors. So let's begin with the first one. For this vector, the length of a vector is also called the norm of the vector. So we can write it like this. It is equal to the square root of the inner product of the vector with itself. And so it's equal to square root of 2, I think, right? 1 times 1 plus minus 1 times minus 1 is 2, and the answer is square root of 2. Great. Now, if I take this vector and multiply it by 1 over square root of 2, I will get a vector which is still an eigenvector for eigenvalue lambda equals -1, because multiplying an eigenvalue by a non-zero scalar does not change the eigenvector. I mean, the result is still an eigenvector, right? But now this time, this new vector will have length 1 over, it will have length 1. So how am I so sure that this vector will have length 1? Well, if I have something that has length, let's say 10, right? By which factor should I stretch it so that the length of that thing will become 1? By factor 1 over 10, right? So in other words, I should not stretch, but squeeze it by 10, but that's the same as stretching it by factor 1 over 10. And so that's what I'm doing here. The vector had a square root of 2 length, and so if I want it to have length 1, I need to stretch it by factor 1 over square root of 2. And you can also verify that if you now take this vector and take its inner product with itself, you will get the answer to be 1. And the same I'm going to do not just for this vector, but also the other one, and this one, and this one. And you can see here, for the first vector here, the length was square root of 2. The same will be for the second vector, but now you can't see, sorry. There we go, here we are. So for the first vector here, the length was square root of 2. For this one, also the length is square root of 2. And for these two, you can see easily that the length will be square root of 4. So that's how we'll have to adjust by the reciprocals of these numbers. We will have to adjust them so that the vectors we get will have all length 1. So now we are ready to write down the final answer, the matrix we were looking for, which will be a 4 by 4 matrix whose columns are orthonormal sequence of eigenvectors of the symmetric matrix we started with. So this is how it will look like. We take the first eigenvector. Well, it doesn't really matter what is first and what is second. There is no canonical order there. I could have taken them in any order, and any answer I would get would still be a correct answer to the question of finding such a matrix. So there are many answers, as you can see. So the first one, I would take just randomly one of these. So let's say I'll begin with the first one I found. So that will be 1 over square root of 2. Okay, so why am I putting 1 over square root of 2 there? Because I'm multiplying this vector by the reciprocal of square root of 2, right? By the reciprocal of its length. So that's the first column. The second column is 0, 0, 1 over square root of 2 minus 1 over square root of 2. The third column is 1 over square root of 4, 1 over square root of 4, 1 over square root of 4, 1 over square root of 4. And the final column is 1 over square root of 4, 1 over square root of 4, minus 1 over square root of 4, and minus 1 over square root of 4. So these are, this is the matrix we were looking for. Great. So just to summarize, the original goal we had was for a symmetric matrix A to find a matrix whose columns are eigenvectors of this matrix, of the matrix A, and which the matrix of those columns of those eigenvectors should have been an orthogonal matrix. So the way we did this was to find the eigenvalues first, and then find the eigenvectors, then adjust those eigenvectors so we make sure we get them orthogonal to each other, and then put them in a matrix. And since we wanted the matrix not just to have orthogonal eigenvectors, orthogonal columns, but the matrix itself to be an orthogonal matrix, we wanted also to stretch each of the vectors there by a certain factor, so we make sure that the length of each column vector is 1. And that's what we did with multiplying with the square roots of 2s and square roots of 4s there. Great.